Certain complex functions are used or required in the solution of biharmonic equation. We covered biharmonic equation last week, and today we will first review certain properties of complex functions and differential relations associated with complex functions. These are functions of complex variables, and a complex number or a complex variable, as you know, is written in this form, x plus I times y, where I is the imaginary unit. For this reason, z equals x plus I times y is the complex variable or complex number, and it lies in the complex plane. This lies in the complex plane, that's z. Now x is the real part. It's shown on the real axis or the horizontal axis. And this y is another real number. It's named as the imaginary part of the complex variable or the complex number. And you can show a complex variable either in Cartesian form or in polar form. And this is the familiar polar form, r times e to I theta, where e to I theta is cosine theta plus I times sine theta. This I is imaginary unit, I squared is -1. So, and it follows, this follows from Euler's formula, that's the polar form. R is therefore called the modulus of z, or absolute value of z. In this case, absolute value only denotes the distance. R is the distance to origin. And theta is the argument of z, and it's noted, again, simply arguments of z. But there are infinitely many arguments for a complex number or a variable. If this theta is an argument, for example, then theta plus 2n pi is also an argument, where n is a natural number. It's equal to 1, 2, 3, and any natural number is n. But there are infinitely many arguments. You rotate and go back to the original location. And there's a principal value of all these arguments as designated by capital A, argument of z, and it's in this complex plane between minus pi and pi. That's called the principal value. This variable, z, this acts as the independent variable in complex function theory. A complex function is a function of this z. Z is defined in a domain. So I will talk about this kind of functions, complex functions. It's a function of z. Therefore, both this complex function and the variable, they are complex numbers. And another definition for a complex function, both the domain and range are subsets of the complex plane. And both dependent variable for the complex function and independent variable, as lowercase z, they can be resolved into real and imaginary parts. Let's say that this is the complex function, capital Z. It's a function of lowercase z. And capital Z is now dependent variable as a function. And lowercase z is the independent variable. Thus, we have this complex function. But both have real and imaginary parts. Z can also be written as real Z plus I times imaginary Z. Now, these are real numbers, real Z and imaginary Z. They are real numbers. For capital Z, the complex function, again, you can find the real and imaginary parts. Real Z is a function of X and Y, the real variables. The imaginary Z is another function of X and Y. You can see that X and Y are real numbers. Real and imaginary Z are real valued functions. Therefore, this is a complex function, capital Z. And these complex functions can be used to find solutions to crack problems, especially a complex function with singularities will have satisfied the condition on the crack plane. But here a somewhat simpler complex function is shown. Complex function Z is Z squared plus 3Z. This is our complex function. And what are the real and imaginary parts of this complex function? To find these, you make the substitution Z equals X plus I times Y, and then carry out the algebra. Z equals X plus I times Y. Substitute here, and you'll find capital Z equals X plus I times Y, squared plus 3 times X plus I times Y. Now expand this, you'll get X squared plus 2IXY minus Y squared plus 3X plus 3I times Y. And separate the real and imaginary parts. Real part, X squared plus 3X minus Y squared. And imaginary part, 2XY minus 3Y. This is the real part of this function. And this is the imaginary part of the complex function Z. Each is a function of X and Y. Therefore, we will adopt this notation. Real Z is now X squared plus 3X minus Y squared. This is also denoted by a function U of XY. And imaginary Z is this function, which is also symbolized by this function V of XY. In other words, Z is U plus I times V. And that's a complex function. Do you have any questions about definition of the complex function? Now, what are properties and differentiability properties, especially, of the complex functions? For this purpose, analytic functions are defined. Analytic complex functions, they can be defined. The function Z of Z, complex function, is analytic in a domain D. This is a domain in the complex plane. If Z is defined and differentiable at all points of D, it should be defined, its derivatives should be defined all points of D. Now, we have talked about singular functions for crack problems, and those are going to be isolated singularities. And they will not affect the general analyticity of the function. Isolated singularities are therefore permitted. But otherwise, the function should be analytic. But we can derive certain differential relations for analyticity of a function so that you can understand whether a function is analytic or not. And those are the rules related to the differentiability of this analytic function, z of z. So what are those rules, or how can we find them? We start with a function, capital Z of z. And we assume that it's analytic in D. It's a function of z. It could be a polynomial type of function or any other, or trigonometric. All have their counterparts in all functions you study in real valued calculus. They have their counterparts in complex theory, but suppose that there is such a function, z of z. Now calculate the derivatives, not with respect to z, but with respect to x and y. What's the derivative of this function with respect to x? And what is the derivative with respect to y? Differentiate by chain rule to find these derivatives. dz dx, for example, is dz times dz dx. And the answer is already given. This is z prime. It's actually an ordinary derivative. And you can use any of those signs. And dz dx is known because z is x plus I times y, and dz dx is simply 1. And for this reason, dz dx is equivalent to dz dz. For any function. Next, evaluate dz dy for this analytic function. What is dz dy? Again, a simple application of chain rule, dz dy equals dz 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 dy. And now we know that dz dy is I, and therefore dz dy is I times dz dz. Now there are two main results here. The first one is dz dx is dz dz. And they are also given here. I'll let you use this. The second one is dz dy equals I times dz dz. Two main results. And how can I derive a condition regarding the analyticity of this function? How can you find a condition for this function to be analytic using these results? How can I find such a condition? Two derivatives, dz dz found from the first has to be equal to dz dz found from the second, because it's an analytic function and the derivative applied in either way should give the same result. I equated these dz dx that should be equal to 1 over I times dz dy, or I times dz dx is dz dy. That is our major result. For this function to be analytic, then we have such a requirement. I times dz dx has to be equal to dz dy. Now, write this in terms of real and imaginary parts of this function, and you can do that. Z is real z plus I times imaginary z. Therefore, dz dx is the real z dx plus I times the imaginary z dx. And you can find the z dy, which is the real z dy plus I times the imaginary z dy. Substitute here. I times the z dx, I the real z dx, minus the imaginary z dx because I squared is -1, equals the z dy, the real z dy plus I times the imaginary z dy. And we equate the real and imaginary parts here, equate the real parts, and you'll get the real z dx equals the imaginary zy, imaginary z dy, and the real z dy equals minus the imaginary z dx. And what are these conditions known as? These conditions are called, you are familiar with these from math course, right? For a complex function or an analytic complex function. These are known as Cauchy-Riemann conditions, are called Cauchy-Riemann conditions. When these conditions are satisfied for an analytic function, and there's a theorem summarizes these results. If z is an analytic function, or if z is analytic in a domain D, then the first order partial derivatives of real z and imaginary z exist and satisfy Cauchy-Riemann equations conditions to all points of D, except for possible isolated singular points. Therefore, these are relations among the components of the derivatives of the complex function. Any questions about these results? Now, a further development related to Cauchy-Riemann conditions is related to Laplace's equation. And we will see what a harmonic function is. So how such results are found? These are related to real z and imaginary z, but let's find that or derive that result. But these are Cauchy-Riemann conditions. If the function is analytic, these should be satisfied. Differentiate the first equation with respect to x, and you'll get d2 real z dx2 equals d2 imaginary z dx dy. and differentiating the second with respect to y, find d2 real z dy2 equals minus d2 imaginary z dx dy. Order of differentiation is not important here. And this is from differentiation in x. The second is differentiation in y. Add them up. These are going to be canceled out, and you'll find this result, d2 real z dx2 plus d2 real z dy2 equals 0. Now this Laplace equation, might recall it, an important financial equation in different branches of engineering, physics. That 2 real z equals 0. That's called Laplace's equation. The real part of the complex function of this analytic complex function, z, it's an analytic complex function. And real part of this function satisfies the Laplace equation. That 2 del squared real z equals 0. And you can also propose this idea for the other components of the complex function, imaginary z. Imaginary z also satisfies the Laplace equation, and you can show it again by starting with Cauchy-Riemann conditions. These are Cauchy-Riemann conditions. Differentiating the first now with respect to y. Then differentiate the second with respect to x, and subtract the second from the first. These are going to be canceled out, and you'll find that del squared imaginary z equals 0. Exactly the same procedure applied here. Second one is subtracted from the first, and we end up with this form. d2 imaginary z dx2 plus d2 imaginary z dy2 equals 0. In compact form, the squared imaginary z equals 0. Therefore, if the function is analytic, function z, if it's analytic, both real and imaginary parts satisfy the Laplace equation. That's the summary of the result, and it's highlighted in this theorem. Second theorem related to an analytic function z. This is real z plus I times imaginary z. Suppose that if it's analytic in a domain D, then both real z and imaginary z, del squared real z and del squared imaginary z. They are 0. Real z and imaginary z are said to be harmonic functions. Harmonic function is a function that satisfies Laplace's equation. For this reason, both real z and imaginary z are harmonic functions. Any questions about these results? Now you have a set of differential relations involving the components of a complex function, as those are real z and imaginary z. And we have also shown that they are harmonic functions. These will be useful in finding solutions to crack problems. especially harmonic functions. Now, further differential relations are going to be derived here for a complex function. And these will have derived the expressions for stresses or displacements, for that matter. And how do we find these? Now, at the very beginning, we determined or found the derivative of dz dx, and we have shown that dz dx is dz dz. And dz dy is dz dz times dz dy. Therefore, this is y times dz dz. These were found. Now, dz dz, this is an ordinary derivative, actually. Let's say that that is z prime. Derivative function, z prime. Thus, it can also be written as real z prime plus imaginary z prime. That is derivative function. And these two qualities will lead to the differential relations we have mentioned here. dz dz is dz dx. Now, dz dz is real z prime plus I times imaginary z prime. It's equivalent to dz dx, which is the real z dx plus I times the imaginary z dx. Now, this will give you two equalities. Equate real parts. Real z prime equals the real z dx. Now, I have a relation between complex derivative and the real derivative. And imaginary z prime is the imaginary z dx. I apply the second one. I times the z dz is I times real z prime minus imaginary z prime is dz dy. The real z dy plus I times the imaginary z dy equates the real and imaginary parts minus imaginary z prime, not this one, minus imaginary z prime is the real z dy, and real z prime is the imaginary z dy. Four equalities or four differential relations that we will make use of later. The real z dx equals real z prime, as from the first equation. The imaginary z dx equals imaginary z prime, again, firstly from the first equation. The real z dy equals minus imaginary z prime, second. And the imaginary z dy equals real z prime, again, second result from the second one. I should note these and use these in our further computations. Any questions regarding these final results or complex functions in general? Now, there's an example on this. Is the following function harmonic? Is the function v equals x times y. And if your answer is yes, find a corresponding analytic function. Now, We know that harmonic functions should satisfy Laplace equation. In this case, which is d2v dx2 plus d2v dy2. That's the Laplace equation. Or del squared v equals 0. This is Laplace equation. I can easily see that this is satisfied because d2v dx2 is 0, d2v dy2 is 0. This is an harmonic function. I can find a counterpart to this to form an analytic function now. I can try to find an analytic function. I'm going to type it here because an analytic function is, we assume that it's u plus I times v. It's typed here. Z equals u plus I times v. Now the imaginary unit is in capital form. There's a capital letter, but v is going to be our imaginary part. This function is the imaginary part. Now find this analytic function. And what is u? Or what's the function? That's the question. How can we find u and the complex function itself? How can we find it?
We can find it using the Cauchy-Riemann conditions.
Yes, that's right. It's an important point, and it's the correct answer. We can use Cauchy-Riemann conditions to find this real part. And I have applied these Cauchy-Riemann conditions. I've written them here. Cauchy-Riemann conditions. The first one is du dx equals dv dy. And the second one is du dy equals minus dv dx. These two will always give you a particular u function. It's important to find the particular function. You don't need to find integration constants. Now, du dx equals dv dy, and dv dy is x. Therefore, du dx is x. Integration gives u as x squared over 2 plus a function of y, as because of the partial derivative. Now you have in general a function of y in such integrations. And substitute this into the second equation. That's du dy equals minus dv dx. Du dy is f prime of y. And f prime of y equals minus y from the second equation. Integrate this, then you'll get f of y is minus y squared over 2. Now, you don't need to add constants at this point. They will not be of any use. It's sufficient to have particular solution. For u is found because f of y is minus y squared over 2. U is x squared over 2 plus f of y. In other words, u is x squared minus y squared over 2. And z is found. Our analytic function, z, is x squared minus y squared over 2 plus I times xy. That was v. But can I write it in terms of the complex variables g? That's the next question. We determine the real functions. U and V. And I write it in terms of the complex variable, yes. But this somewhat trial and error technique, but there's a systematic way of finding these two. If you try z squared over 2, for example, it's x plus iy squared over 2. Expand this, x squared plus 2ixy minus y squared over 2, and it's exactly the same as our function. Our function is z squared over 2, but I cannot know it in advance. This might require some trial and error estimates, but there's a systematic way of finding it as well. You consider the complex variable and its conjugate. Now, we know that z is x plus I times y. Complex conjugate of z is x minus I times y. If you solve this as a linear system for x and y, you'll get x 1 over 2 z plus z bar. Z bar is the conjugate. Y is 1 over 2i z minus z bar. And substitute x and y into this zone. X squared minus y squared over 2 plus I times xy. Substitute x and y here and simplify this. Sorry, not here, we are here. X times y then becomes, after this calculation, 1 over 4i z squared minus z bar squared, and x squared minus y squared over 2 after simplification becomes 1 over 4 z squared plus z bar squared. Thus, this is u plus I times y. Z bars are cancelled out. And you simply have, these are cancelled out, z squared over 2 as the analytic function. Now, therefore, we could manage to derive this analytic function. And the starting point was this question. We were given the imaginary parts of the analytic function. This is harmonic. And Cauchy-Riemann, by applying Cauchy-Riemann conditions, we determined u and then the value of complex function as z squared over 2. Any questions or comments about this example? Now we will apply these properties of the complex function in solution of system problems and particular crack problems. And I'm going to talk about this in the next lecture.